Hello. As part of the Micro and Smart Systems course, today we will start a new topic, and that is the modeling of solids. What makes microsystems different from microelectronic circuits is the movement of the solids and the flow of the fluids. So, we have solids and fluids which move and give the functionality to microsystems. Here in this series of lectures, we will look at how we can model the moving solids. The solids can move in two fundamentally different ways, and they are: one is the rigid body motion. By that what we mean is that if I have an object that can only translate in two directions and also can rotate, that we call it a rigid body motion. But if you want to define rigid body motion, a good definition would be that if you take any 2 points in the solid, then as the body moves, the distance between those 2 points will not change. Let us look at the picture that is shown over here, which has a body with 2 dots shown on it. These 2 dots, let us magnify it a little bit. Let us go to the page width. No, that is not enough. Okay. So, if you look at this body here, which is shown in dashed lines, and it has been moved to another location where it is shown in solid lines. If I look at these 2 points, before it moved and after it moved, the distance between these 2 points will remain the same if the movement of the body is called a rigid motion. Likewise, if we have a rotating body as shown in the diagram over here, we have again taken 2 points on this body, and this has rotated by a certain angle, and we look at the same 2 points in the rotated position. When the distance between these 2 points remains the same, under the rotation also we have rigid body motion. There are a lot of examples around us which indicate this type of rigid body motion. If you look around, I am sure you will find an example of a rigid body motion around you. For example, if I just take my eyeglasses, the hinge motion that is there in this eyeglasses, in this pair of eyeglasses, is a rigid body motion, because if I take any 2 points here, the distance remains the same as the body is moved. That is one way solids deform, and another way is where this distance does not remain the same, and that example is shown over here. If you look at this picture, we have a rod and we are applying a force, and in the process we have stretched it. If I were to take 2 points in the original position, when it is stretched, because the entire bar is stretching, distance between any 2 points will also increase here. So, it is not rigid body movement. There is what we call elastic deformation of the body that is taking place in this example. Likewise, if I take the same body, I indicate 2 points on it and I apply a force in this direction. When I do that, then this bar is going to actually bend. We call such a thing a beam. A beam under the transverse force, that is the force acting in the direction perpendicular to the axis of the beam, then the beam will bend. When it bends, the distance between these 2 points would have changed. So, that is also not rigid body motion. So, we note that solids can deform in 2 different ways. One is rigid motion, other is deformation. Rigid motion are the example shown here, where as you rotate or translate, the distance between any pair of points does not change. That is the definition of rigid body, and whereas in the deformation things will be different. That is, any pair of points you take, the distance need not be equal, and such a thing we call an elastic body. We are all familiar with a lot of elastic bodies. If you take a piece of paper, you can fold the paper, that is also a deformation. If the paper comes back to original state, we call it an elastic body. So, a lot of elastic bodies around us. So, these are the two things that we need to keep in mind as we proceed to work towards the modeling of solids. Let us look at some examples of microsystems devices in order to get motivated to study the deformation of solids. The rigid body motion of solids is important, and there are a few microsystems devices where you need to study the rigid body motion of solids, but many other microsystem devices undergo elastic deformation, and for that purpose, if you want to model them, we need to look at elastic deformation of the bodies. So, here is an example which is called a folded beam suspension. So, we have 2 points here, this portion, not points, this portion and this portion. When we anchor them, when we fix them, this entire thing can move relative to these 2 points. That movement will happen because the beams that are here, there are 4 beams here and another 4 beams there. Only because of the deformation of these beams, the central I-shaped mass or a solid portion can move only when these beams bend. So, there is one example of elastic deformation that gives the motion. And if we ask the question, if I apply certain force here, how much displacement do I get here? Sorry about that. Let me turn off my mobile phone. Okay, coming back to this example, when we have a mass with 8 beams connected in this fashion, whenever there is a force applied, we would like to know how much displacement this body undergoes. So, for that we need to study the elastic deformation of these beam like structures. Another example, if I take a suspension which is a different kind, here we have a central platform circular in shape here, and we have a outer platform, and we have beam like structure connecting the central platform to the outside one. In this particular case, I can use it to raise the central platform up and down relative to this outer platform, so that I can have it like an x, y or z stage. I can move it in the x direction, y direction as well as up and down. So, if I again ask the question, if I were to apply some force in the vertical direction, how much does it move? We need to study the deformation of these beam like elements. Let us look at one more example where we have a suspension which is a different kind. Suspension, we call it suspension because the central mass which we call proof mass, that will be able to move in the x direction, y direction, and that is given by the suspension. These beams 1, 2, 3, 4, 5, 6, 7, 8, that is 4 pairs of beams suspend this mass in such a way that it can freely move in x and y directions, but will have difficulty to rotate. Such a platform, I have it here which I will show. If you see here in this particular device, we have a suspension. If I move it in this vertical direction like this, you can see it moving, and you can also see some of the beams. Observe here, for example, these beams are deforming. They are not just rigid body movement, their motion is not just rigid body movement, but actually deforming, as you can see. Similarly, if I apply force in this direction, there are these beams that are deforming. So, this has perfectly decoupled motion in the x direction and y direction. What we have here on the screen is also a suspension similar to that. So, if you want to know again, if I apply certain force in the x direction, how much does this proof mass move? Again, we have to study the deformation of beams. Let us consider one more example before we begin to study this. So, here you see an eye of the needle, and within that we have lot of these micro mirrors. One of them is shown in a close up view. This particular mirror, its schematic is shown on the left side, and here we have the serpentine beams as shown here, each one of those 1, 2, 3, 4. 4 of these have these serpentine beams, and they provide this central mirror an ability to rotate about two axes, about x axis as well as y axis. If I call this x axis, it can rotate about that. If I call this y axis, it can rotate about that as well. Again, we need to study how these beams deform in order to solve problems of this kind. With this motivation, let us begin with something very simple. Let us take a bar . Let us take a bar like that. Let us say that it is fixed at this end, and let us say this is the axis of the bar, and we apply a force in this direction. Okay. Let us draw a straight bar. Okay. When I apply a force here, let us call that force P. Okay. And if I cut here, I will see, if I look in this direction, I will see certain cross section. Let us call it a circular cross section of area A. Okay. So, I have taken a bar of circular cross section, applied a force P. When I take a section here, that is how it is going to appear, right. Now, what will be the force in this section? Because this section, before it was cut, it was held to, it was holding together the two pieces. So, the piece here 1 and 2, if I call it, let us draw this piece 2. Imagine that we have the bar and we have made a cut over here and separated it. We have a force P on this side. We should have a force P on this side also. Only then the bar that is cut is going to be in equilibrium. This is sum of forces in the x direction has to be 0. So, if I cut, let us say over here and take a small piece there, again we will have the force P and force P here. So, the force at this section will also be P, at this section it will be P, or if I cut there, we have to take a longer length of the bar. Again for that we have this P and we have this P, and on this also it will be again force is P. So, anywhere I take along this bar, if I cut it, my internal force is going to be P. We now define a concept of stress, because a bar that is under some loading is going to experience some stress. That stress is defined as force per area of cross section, area of cross section. Okay. So, if I indicate with what we have the symbols, the force we have applied is P and area of cross section is A, and the symbol that we use for stress is sigma. So, sigma is a stress which is force per unit area. If I take force divided by area of cross section, I get the stress. Okay. So, stress is something, a quantity that we define to understand the effect of a force on an elastic body. You cannot see stress. Stress is a concept you have to imagine, understand that whenever we take an elastic body, apply forces on it, it is going to experience some stress. But what we can see is what we can call strain. Okay. Strain is defined as the change in length, divided by original length. Okay. And we use this symbol epsilon to indicate strain. So, epsilon is a strain, it is defined as change in length by original length. If we go back to our bar, let us draw it again. We are fixing the bar at one end and applying a force P. because of this force, the bar is going to expand a little bit. Let us say the bar has moved here. So, this quantity, let us call this delta, this expansion of the bar. When you pull on the bar, it is going to change its length, it is going to increase that length by an amount delta. So, if we go back to our strain definition, I would put that as delta divided by the original length of the bar, let us denote by L. So, that is L here. So, the strain is going to be delta by L. So, now we have defined two quantities, one is stress, which we denote by sigma, which is P by A, force by area of cross section, and then we have defined another quantity strain, which is delta by L. These two are related because of the nature of the material, and that goes under the name of Hooke's law. Robert Hooke, who proposed this law, he found out that the stress and strain are proportional to each other. So, stress here is proportional to strain, and the constant of proportionality is called Young's modulus. So, Y that we have used here is called Young's modulus, which is the property of a material. So, if I were to draw this stress versus strain, at the beginning this curve is going to be a straight line, and the slope of this is Young's modulus y. Now, let us relate using this Hooke's law, which is this, by substituting for stress and strain in this bar. So, if I do that, sigma, let us rewrite it, sigma y times epsilon, sigma is P by A and y, epsilon is delta by L. So, what we find here is that delta can be written as P times L over A y. So, the elongation or contraction depending on the sign of P, the change in length of the bar, that we have taken is given by this formula. But note that this is not a formula that we need to memorize. It can be derived, if we go back, by considering equilibrium of the segment that we cut at every point, so that we will know internal force acting at each point. Once you know internal force, you use the definition of stress, force divided by area of cross section, and the definition of strain, which is change in length original length. By using these and Hooke's law, which tells you how the material is going to vary its stress and strain based on a property that we call Young's modulus, we can derive this formula rather easily. As we will see, as we consider more complicated elastic bodies, the bar, by the way, is the simplest elastic body that one can imagine. It can only axially stretch and contract. If we take more complicated elastic bodies, our principle is still going to be the same. We use static equilibrium, so that all forces are balanced, and later on we will also have to balance what are called moments. After that, we use our definition of stress and strain, and then relate stress and strain based on the property of the material, which is Young's modulus, and we can compute the elastic deflection as shown here. Let us look at a case where we have the same bar, where again we have the normal stress. By the way, this is called normal stress because this stress is going to act normal to the surface of the body. So, we have the body where we have cut and it is going to act normal to that. That is why it is called a normal stress. If there were to be two forces as shown, there is a P1 here and there is a P2 here as shown in the bar over here. When you have such a situation, the internal force is going to change. Let us go back to the pad and then see what is going to happen. So, now I am going to take a bar. Again, let us consider the fact that it is fixed at one end. Now, I say that there is one force here, let us call this P2, and then somewhere else at this point I have a force P1. Okay. Now, let us take sections of this bar. If I were to cut over here and separate out the segment, the internal force that is going to act at this section is going to be just equal to P2, because only then this bar will be in static equilibrium. Static equilibrium. Okay. Whereas, if I cut somewhere here, if I draw that piece of the bar, so I have P2 here, but somewhere here I also have P1. So, this force that is going to balance the forces P1 and P2 has to be P1 plus P2. So, in this case it is going to be from here to here, it is going to be P1 and then it is going to be P1 plus P2 from there to there. So, the stress need not be same in an elastic bar when there are different forces or if it has different areas of cross section. So, here if I go back, for this portion the stress is going to be P2 divided by area of cross section, this is the stress, whereas for this portion the stress is going to be P1 plus P2 by the area of cross section. Okay. So, because of this we have to keep in mind that whenever there is an elastic body, when there are different forces acting at different points, our stress is going to be different, because the force, internal force might be different. We can also have a situation where I can have a bar with change in area of cross section. Okay. So, we have here a bar which is, let us say, fixed at this end, area of cross section here is A1, area of cross section here is A2, this is a smaller cross section, A2 is less than A1 if we have that. In this portion anywhere, let us say we have a force P acting on it. In this portion the stress sigma, normal stress sigma is going to be P divided by A2, whereas in this portion the stress is going to be the same force P, because if I take a section here it will be the same force acting on that, but area of cross section is A1. If we call this sigma 2, we will call this sigma 1. So, when there is change in area of cross section, again the stress will be different at different place in the bar. There can be an additional force coming in, internal force may vary or area of cross section may vary in order to change the stress. So, this is about the bars, and the bars happen to be in microstructures in many different places. Let us take for example a resistor which is shown in a figure here. If I take a resistor like this, resistors are very common, there are conductors, resistors all over the integrated circuit chip as well as microsystems chip. When you have something which is fixed at both ends, so far we considered bars which were free at one end where we can apply a force and other end it was fixed, whereas here we are fixed at both ends and here we have actually applied a voltage potential so that current can pass through that. When current passes, it is going to get heated. Because of the heating, most of the materials will expand. When they expand, they want to change their length, they want to increase their length, but it is fixed at both ends, so it cannot. In that case, the material inside will develop a stress, and that stress in this case will be will have to be compensated by the stress created by this bar. If I take a normal bar if I take, let us say, the same resistor, which is a bar, which is fixed now at both the ends. Okay. Now, I heat it by a temperature, heat by temperature delta T. When I do that, this bar wants to expand. How much will it expand? If it were to be free, let us say I take this to be fixed at one end, it would have expanded by an amount which we can call delta, that will be given by the length of this bar L times alpha times delta T. Delta T is the rise in temperature, that is what we have indicated over here. This alpha is a material property called thermal expansion coefficient. Okay. So, if we have a bar of length L, if we heat it by a temperature delta T, if it is were to be fixed at one end, it would have expanded by this much. This thermal expansion coefficient is the elongation of a material per unit length per unit temperature rise. We want the total elongation, we will multiply by the length and the change in temperature. But now, since it is fixed over here, it cannot expand. So, it will have to develop a strain to compensate this. That strain, which we will call thermal strain, okay, in this case has to be negative L alpha delta T, that is a change in length divided by the original length, which is L, which will be minus alpha delta T. Alpha is the thermal expansion coefficient multiplied by the change in temperature. This is the thermal strain. Thermal stress will be what we have written earlier, Young's modulus times the strain, which in this case is going to be minus y alpha delta T. That will be the thermal stress. Whenever the stress has a negative sign, we call it compressive stress. Compressive stress. Okay. If it is positive, we call it, this is negative. If it were to be positive, we call it tensile stress. So, we have compressive stress here and tensile stress. Okay. So, a bar can also have loading, not just thermal loading, but also we can have the mechanical load. It can come with active materials, can have different stresses and strains. Whatever it is, we can relate it. If we know that it is linearly proportional, we can relate it with Young's modulus, but sometimes this relation may be even non-linear. The stress strain relationship may not be linear, non-linear, then also we can deal with it. That is what we can say about bars. Now, let us look at the next case, where instead of having a bar, just one bar, let us take a mass as shown here connected with two bars. So, we can get stiffness of this bar and this bar as shown here. If I say the first one, we have a stiffness indicated as K, which is given by area of cross section y times L. How did we get this? Let us define what stiffness of the bar is. So, if I have a bar and I fix here, what do we mean by stiffness? If I apply a force P, let us say the length here is L and the area of cross section is A. Okay. This is area of cross section A. If it is made of a material whose Young's modulus is Y, we just derived above that the expansion of this bar, which we can call delta, that was given by P times L by A y. That is what we derived above. Now, what do we mean by stiffness? Stiffness is the force, which in this case is P, divided by the elongation delta. What is P by delta? In this case it will be A times y by L. So, P, I bring delta this side and A y goes there, L goes here, we get P by delta equal to A y by L, which is also called the spring constant of the bar if we were to represent this bar as a spring. So, if I take this bar, I can say that this bar is like a spring and I have a force P, then it would deform by an amount delta with this force P. The P initially equal to 0 and P goes to some value from what the bar was here will move to this point. Okay. So, here we denote this as K, the stiffness of the spring, that same thing as stiffness of the bar. So, the entire bar we can represent as one single spring and the stiffness of the spring is given by A y by L. So, when we go back to the example that we consider here, if I have a mass where there is certain acceleration A of x acting on it, it will have a force which is mass times acceleration. In this particular case, the mass, okay, here is the example. We want to take a mass of 50 microgram acting on a body. Okay, the body here is some square mass, it has 50 microgram, that is 15 to the power minus 6 kilogram, and it is suspended with two bars of length 100 microns, but different areas of cross section. One is 4 micron square, other is 25 micron square. The smaller one is 4 micron square, larger one is 25 micron square. If I have this, then I can represent this particular thing as a mass suspended with two springs. Okay. So, just as we have done for the previous one, now I have a small bar and a large cross section bar, and each of these are connected to a big mass. So, this is fixed here, this is fixed here, area of cross section A1, area of cross section A2, we have the mass on which there is the force m times acceleration. Okay. So, this can be represented as two springs and there is a mass here. Okay. So, if I fix the spring, I can have spring constant K1 for that, K2 for this. These two springs are said to be in parallel. So, these springs are in parallel, springs in parallel. That means that they share the same displacement, that is they have the same displacement, whatever this spring elongate, this spring has to elongate by the same amount, and they will share the force applied on this. This ma is the force here, that force is shared by these two, that F that we have. So, we saw earlier that the spring constant times the delta is going to be equal to the force. Okay. So, let us write that. So, we have the force is equal to spring constant times deflection of the spring. Okay. This is the force F, spring constant K times the deflection delta. Okay. So, now when we have two springs like this, there will be a force acting this way, which is K1 times delta. If we denote the movement of this mass as delta, there will be K1 delta and K2 delta, which we will do it here now again. Let us draw this mass and show this spring of constant K1, another spring of constant K2, which are both fixed here, and there is a force F acting here. If I were to break away these springs, then I can put the mass and there is a force acting on it, and there will be a force which is K1 times delta, another one K2 times delta. So, that means that K1 plus K2 times delta is equal to the force or the new spring constant, which is F over delta. The new spring constant, which is F over delta, is equal to K1 plus K2. In other words, this thing I can show it as a single spring which has a stiffness K1 plus K2. So, springs in parallel will have their stiffnesses added in order to get the equivalent spring constant. Now, if we go back to this example, we have two springs of spring constant K A1, K A2, because of the area of cross section is different for these two parts. One turns out to be, because it area of cross section 4 micron square times length 150 micron square, which is specified in the problem, and Young's modulus 150 gigapascals, that is Y is given as 150 10 power 9 Pascal, gigapascal is 10 power 9, that is Y, and the length is 100 microns, then I get 6000 Newton per meter stiffness, and another one 25 micron square cross section 150 gigapascal for Young's modulus divided by 100 micron length, I will get 37,500 Newton per meter stiffness. So, when we know the total force acting on it, we can divide this force by K1 plus K2 and get the deflection for this mass. If we take a different scenario, we put a narrow bar over here and a wide bar over there, even then the two springs have the same force acting on them, because the same force will act through this bar, same force act with this bar, again these are in parallel. Whereas, if I were to attach the springs end to end as shown here, the narrow spring and wide spring, I am calling it a spring even though it is a bar, because a bar can be represented like a linear spring, and attach the force here, then the force that we see in this bar as well as in this bar, the force is going to be the same, whereas the deflection is not. In these two cases, the deflection is the same here and here, because in this case both are elongation, both are contraction. Here one will be, let us say if it force is applied in this fashion, we will have the compression of this bar, elongation of this bar, both magnitudes will be equal, then we call them springs in parallel. Whereas, if they have the same force, then we call them in series, in which case displacement will be different. This portion will deflect something, this will deflect something, the mass will be the total of these two deflections. In that case, we call them springs in series. In that case, what we will have is a situation that is slightly different from springs in parallel. So, if I have two springs as shown in that picture, let us call this K1 and another spring, this is K2, and if I have a force applied over here, this will deflect, let us say an amount by displacement x2, this is x1, the deflection in spring 1, this is the deflection or elongation in spring 1 is equal to x1, because that is what this point is going to move, and the deflection in spring 2 is going to be x2 minus x1. Okay. This is elongation. When we say deflection, we actually mean it is elongation, how much the spring is going to move or increase by x1, x2 minus x1, they are not the same. So, the springs in series, but the force is the same. So, we will have the force F is equal to K1 times x1, and it is also equal to K2 times x2 minus x1. The force is the same, but deflections are different. In this particular case, what we get is that the equivalent spring constant, if we solve these two things, we get that the K, that equivalent spring constant equivalent spring constant will turn out to be harmonic mean of the two springs, 1 over K1, 1 over K2. In other words, the K is equal to K1 K2 divided by K1 plus K2. Okay, 1 over K, here we will have K1 plus K2 by K1 K2. If I take reciprocal, I will have this. This is what you get for springs in series. So, this is something we need to remember when there are elastic body. If we can break it into little pieces as shown here, we can get equivalent springs and combine them together to get the total spring constant. Now, let us move on to the next level of detail, which is bending of beams. In the case of bending of beams, shall I continue?
Yes, sir.
Thank you. Okay. Now, let us move on to beams, where a beam is going to bend as opposed to just stretching or contracting like the bar did. In the case of beams, we need to define a few more quantities and what kinds of stresses will act when a beam bends. So, we have a different kind of a suspension. We have a mass here and the beams. When there is acceleration in the x direction, these beams will only experience axial stresses like bars we just did, but when there is a force or acceleration in the vertical direction, then these will deform as shown here. In order to look at those things, we need to again take the beam and show the forces. Now, the forces are going to be perpendicular to the beam. So, if I take a beam, let us say that I show a beam which should be what we call a slender beam. In the case of bars as well as beams, we want it to be very long compared to its area of cross section or the dimensions that define the area of cross section. In the case of beams, if you want to apply the theory that we are going to develop, we want the length of the beam L, okay, and let us say we take a certain cross section. Let us say this has a cross section that is rectangular. If there is width W and the height H, we want the length to be more than at least 10 times or 15 times 10 or 15 times the maximum of W and H. If this is true, we call it a slender beam. In such a slender beam, if we have a force F acting in the vertical direction, which we call transverse direction, what is going to happen? This beam is going to bend. So, in order to analyze that bending, what we will do is we will take a piece of the beam. Let us draw that slender beam one more time with a force acting. Okay. I take a section here like we did for the bar, but in the case of bars the force was axial in this direction. So, we were able to just say that is the force. If you recall, if I take axial force, if there were to be force in this direction, which that is the force, we had P, but now we have a vertical force which we are denoting by F, transverse force. In this case, if I were to take this segment of the beam, okay, there is a force F that is applied, what will happen here? And that will have a force that is in the vertical direction, which we denote as shown in the picture here, okay, which is a vertical shear force, because the effect of this is to shear this material. So, this is our vertical shear force, which happens to be equal to F in magnitude, because this is up, this is down, this is in equilibrium as far as the forces in the y direction, that is y direction here. So, now we need to denote all the things. This is our y direction, this is our x direction. The force in the y direction sum, this has to be F to compensate for that one. But if I take moment about, let us say, this point, this vertical shear force does not contribute any moment, whereas this will contribute. Let us take this length to be okay, let us denote where we have cut this distance as x. So, this is going to be L minus x. So, this is the distance which is L minus x, because the total is from here to here is x, the total length we take it as L here. So, there is L minus x. If I take moment of this 4 times L minus x will act like this, and this we call the bending moment. It is this moment that tries to bend the beam, this moment. So, that in this particular case will be equal to this F times L minus x, that is a bending moment. Okay. As we move from this end to that end, when we go here, L minus x, x is equal to L at this point. Okay. Let us say this point, x is equal to L. So, there will be L minus x 0, no bending moment. As we move towards this, bending moment is going to increase as x becomes smaller and smaller. As we go from here to here, the bending moment is going to increase. In fact, we can draw this bending moment diagram for this and also shear force diagram. So, which is shown in this picture over here, the left side picture. As I take sections at different points, I will see that this vertical shear force V remains constant, that turns out to be just V all through from x equal to 0 to L, whereas bending moment will be 0 here, this is L minus x, this is 0 there, and then as we go it is going to be minus F over L, because our sign here, whenever there is movement this way, if we go back and look at the sign of the movement here, this is going F times L in the clockwise direction, this has to be counterclockwise direction. We say that bending moment is negative, and that is indicated over here, that is our sign convention. Bending moment is negative for something like this. When I apply force, it is going to bend like this in a convex fashion, and that is the negative bending moments effect. Like we had in the bar, if there were to be two forces, then there will be a change in the vertical shear force, just as in a bar there was a change in the axial force or internal force. If I have F1 here and F2, up to this point there will be just F1, vertical shear force V is going to be just F1, and after that it is going to be F1 plus F2. If I cut anywhere here, it has to compensate this force, and I will get this vertical shear force in this fashion. And likewise the bending moment too, when I cut from here to here anywhere, the bending moment is going to be F1 times L minus x. So, that will have certain slope here. It will reach a value minus F1 times L minus a if I indicate this distance as a. I am coming from x equal to L back to x equal to a, decreasing x value, because I am moving towards this x equal to 0 at this end, and after that I am going to have a bending moment which is F1 times L minus x and then F2 times A minus x. So, together from this point onwards there is movement due to this force and this force, which this bending moment has to compensate. It goes like this and it reaches a most negative value minus F1 times L plus F2 times A, that will be the bending moment. So, given any beam, we can draw the shear force diagram and the bending moment diagram and try to get the first the effect of shear and then effect of bending on the bar as x varies from 0 to L, how they change, and we have to consider what is the effect of bending moment. As we just said, effect of bending moment is to bend the beam and shear force is to shear the beam. We will consider shear effects later, but let us look at what is the effect of the bending moment. For this, let us consider a small straight segments which is under what is called pure bending. That is, there is a bar and we are applying moments that tries to bend the straight bar into a shape that is shown here. If that bent bar has a radius of curvature rho, because it will bend into a circular arc shape, the straight one has become a circular arc shape that has a radius of curvature rho and an angle theta at the sector that is shown here. If I take radius of curvature from here to here and here to here, this is the center of curvature, angle subtended by this bent bar is theta. Then we look at this cross section and we define what is called a neutral axis, which is shown as a dashed dot line in this figure also. Neutral axis is a line within this bent beam where the beam does not extend, does not contract. In other words, it remains in the same length, and the ones above the neutral axis will have to decrease in length, the ones below neutral axis have to increase in length as the beam bends. So, let us look at that here. So, we have taken a straight beam and we have rotated by applying moments, bending moment for this. We applying bending moments to rotate it into a circular arc where there is center of curvature and rho, which is the radius of curvature. We are saying that there is going to be an axis which will neither stretch nor contract, which we will call neutral axis. Okay. If you have neutral axis, any fiber, if you will, if you take that and look at it before, the ones above have to contract. So, this portion will have to contract and this portion has to stretch. Okay. If I take a small fiber here, if I take the same one, it would have stretched, whereas if I take a small one over there, that would have contracted. So, the one above this portion, that will be under compressive stress, where the normal stress has a negative sign, whereas this portion will be what we call tensile or positive stress when the beam bends in this manner, whereas this will be negative stress. Okay. So, for the case of beams, we need to discuss a little bit more as to how to get this stress that is above, which is compressive, below the neutral axis, which is tensile, and we have to relate it to the forces that are applied, because if we go back to our problem, we have the beams which have a transverse force acting. So, this is the kind of thing we are looking at, and how do we determine this bending, which we will discuss in the next lecture. Just to summarize what we have discussed today, we first discussed what is meant by the motion of solid bodies. It can be a rigid body motion or elastic deformation, and then we looked at the motivating examples which we will revisit in the next lecture as well, and we discussed at length about how bars axially deform, and then we discussed the concept of normal stress and normal strain and Hooke's law, with which we can determine the deflection acting in a bar that is subject to axial loading, which is given by load times length of the bar divided by Young's modulus times area of cross section. We also discussed how thermal loading will cause stresses inside bars, and we considered bars in parallel and series, which are like springs in parallel and series, where we have shown how a bar can be treated like a simple spring, and we moved on to beams and defined the concept of the vertical shear force that we see whenever we take section or bending moment in order to keep the broken piece in equilibrium. It has to be in force equilibrium as well as movement equilibrium. We will consider how the beams bend in the next lecture.